Hello, everyone, and welcome. Thank you for joining me on this damp day. Well, at least it's damp in Berkeley. Announcements, congratulations on the midterm. You guys have done very well thus far in the class, and not just on the midterm exam, but throughout. You've been working hard and turning in your stuff and doing well. Regrade requests are due this Friday. The ed post is linked there for the process. And that post also has a summary of the performance thus far. Let me see. There's a new set of tutoring signups. We always start afresh in the second half of the term. And so those have been released, and there's an ed post about that. No homework is due this week, so there's nothing due tonight or tomorrow. But on Friday, we'll release a short project as well as a short homework. And I have a little note about my own morning office hour today. My office hour that is directly after this class, this one will be online. Instead of in person. I didn't want you guys having to trudge out in the rain. So since these are individual office hours, if you want to see me during this time, please send me an email and I'll send you your own link. My evening office hours are going to be just the same, and those have always been open and those have always been online. Can I just take, Will and I will just take questions for 1 second about any logistical issues or any such questions that you might have. All right. So the goals this week, on Monday, we learned a formal and consistent definition of percentiles. We learned what a bootstrap is, and we learned how to use percentiles and the bootstrap for estimation. And today we are going to do a quick recap of that. These intervals of estimates that we came up with are called confidence intervals, and they perform certain functions, but they're very tempting to use in ways that they should not be used. So we'll talk about interpretation. And this is one lecture, which if you watch the video, it is a really bad idea to fast forward through the talking, right? Because today, I believe the code is going to be straightforward, but it's the interpretation that is the key. By the end of today, you'll have a very clear sense that we need to be able to talk more precisely about what we mean by center, what we mean by variability, and so on. So Friday, we start that. And the aim there is not to just give you, here's a measure that you should compute, but why that measure rather than any other? Because you can come up with many different ways of defining center and spread. So that's the goal. We'll start today by a recap of where we were. Okay, so we use words like inference. I just want you to remind you is inference is making a conclusion about something unknown based on what you can see. And so pre-midterm, the inference that we were doing was always like this. You have data in a sample, and you are trying to make some conclusion about the process for generating the data. And this method of inference was called testing hypotheses. Now, what we're going to do is we're going to say, okay, there is some population, there is some underlying distribution, and there's a number associated with that we're interested in. For example, the population is all US households, and the number we're interested in is the average household size. In a US household, on average, how many people there? And we want to know that number. Now, in principle, we could go find it by talking to every single US household. In practice, that's impossible to do. So we have to estimate that. And so what we're talking about now is about estimating numerical parameters. So parameter is a fixed quantity in the population. This is not random. Even though you don't know it, at the moment, the approach that we take is it is fixed. And so the question is, how do we figure out the value? And, we're realistic. We know that we won't be able to figure it out exactly based on incomplete information. So we have to figure out what can we do. If we have a census, then we can go and calculate the number exactly, but we typically don't. So we take a random sample. We take a random sample and a large one, because that we know by law of averages should resemble the population, at least with high probability. And then we compute a statistic in there that we hope that will be a good estimate of the parameter. And all these words like good and so on need quantification, which we're going to do gradually over the rest of the semester. So we know that one random sample leads to one estimate, and we know we have tons of experience now that says if the sample had come out differently, then your estimate would have been different, and we have to account for that when we provide the estimate for somebody to use. So we need more than one sample. And so the question is, where do we get another sample? To see the variability, we need lots of samples. Why can we not go back again to the population and just take another sample? We took one. Why can't we take another? Usually, what's the reason? Money and time, resources. That's the reason. Exactly. That's why we took a sample in the first place, right? Because we didn't have the money to go and ask too many questions of too many people. So there is this wonderful method called the bootstrap that says, look, you can't go back to the population, granted, but you have a large random sample, and the reason you took that was with high probability that large random sample looks like the population. So how about sampling from that? And that method is called the bootstrap. And the bootstrap works for a reason. This picture should be sort of imprinted in you, which is that you have a population. If you draw a large sample from that, you can see the large sample looks like the population, not always, but with very high probability. And then if you sample from that sample, then all of the samples from the sample will look like the sample. So all of these will resemble each other. Okay. So somebody has asked a question which says, what if we didn't have the population in the first place? If you didn't have the population in the first place, then you can't move, right? Because that you have no hope of trying to estimate that parameter, because you can't even draw your original random sample. So somewhere there is a list of the population. That is the premise that we are starting with. And we have the resources, this is a realistic situation, to draw one large random sample, but that's it. Okay, so now there's the question, if I'm sampling from the sample, I have to decide these resamples, as they are called. What size should they have? Could somebody explain to me what size they should have and why? They should have the same size as the original sample. Why is that? So to compare them, exactly, because you are going, these are your data, you are going to make the variability in these data should be reflected in what you are drawing the next time. And you have, I think, an instinctive sense that the sample size affects variability, it affects accuracy. So for now, hold on to that instinctive sense, it is correct. A couple of weeks down the road, we'll have more of a quantification of that. But yes, you sample the same size as the original sample so that your samples are comparable. And so now you have to make a decision. You can sample without replacement or with replacement. Which one are you going to do? With replacement. What is the problem with sampling without replacement at this stage? You just get the same values again because you're taking the same size. You'd get exactly the same sample. That won't help you, right? So this little change, sampling with replacement, gives you samples, as you can see in the picture, that are very similar to what you had before, but just still a little bit different. They're different samples. So you can get estimates from them. And so typically you won't be able to see the parameter. You'll have this one sample. You'll generate a whole lot of samples from that. From each of those samples, you will make an estimate, and then you will have an empirical distribution of that. Okay, so the key to resampling is you draw at random with replacement as many values in the original sample, and you need the same size. And so what I'm going to do today is I'm going to start with where we were. last time. And so we had a table of salary data, actually, with approximately 37,000 employees in San Francisco. And their total compensation histogram looked like that. And we decided that the parameter that we were interested in is the median of these total compensations. And this was an ideal scenario in which we have the entire population, so we can actually see what the parameter is. Okay, so really, realistically, we have no need to estimate this parameter. If you actually know the parameter, you're not going to spend the time estimating it. But we, for understanding how the sampling works, are going to draw samples and then see how our proposed method works out. And so we did that last time. We started with a sample which I took to be without replacement. And there were a number of questions about this on Ed and in the chat. So I want to talk about this sampling here. You actually have the choice. You should take it to be large so that you have some, reasonable possibility that it looks like this population. With replacement or without replacement, in this situation, you have the choice. Why? Without replacement is more natural. However, if you sample 400 out of how many, 37,000, with replacement and without replacement aren't that different. Why is that? Can somebody explain? You have this huge population, you're taking out 400. Actually, no, the chance is low to repeat. The chance of repeat is low, and that is because the size of the sample, though absolutely it is large, relative to the population, it is very small, right? What happens when you sample without replacement is that the composition of the population keeps changing every time. But if you're only taking out a tiny number compared to the big population, that change is not perceptible. No, this is not the law of averages. The law of averages is a large sample thing. We're actually talking about a sample that is small relative to the population. Right? If you take out 1 out of the 37,000, then you change the population a little bit, but not by very much. Even if once you've taken out 350 out of your 37,000, you haven't changed the population by very much. So that becomes very much like sampling with replacement. Don't worry about it. Don't worry about it. There are no hard and fast rules, but if you want, you can start with a with replacement sample, that's fine. My point is that in this situation, they're going to be probabilistically almost the same. So we took the natural sample and this one turned out to be like this. And so, okay, here's our sample and it kind of looks like that, but not exactly. And so, but this one has some median, except that that's, not going to help us. We need a whole bunch of them because they vary. And so we're going to bootstrap this. And so we're going to sample randomly. We're going to sample randomly from the sample, which we're calling our sample with replacement, the same sample size. And so the key move in any simulation is simulating one value. All right, so this is where you have to pay attention. We said we were going to sample from the original sample. That's called our sample, and so therefore that's the table. We use dot sample on that table. There are no arguments in the dot sample. Is that because we don't care? It can be anything? Or why is it? We want to sample, okay, with replacement is the default. That is what we want. And by default, the sample size is the same as the size of our sample. That is also what we want. So by default, dot sample does exactly what the bootstrap needs. And that's why we don't have to put any arguments in there. And now what we have to return is a statistic. A natural statistic is to calculate the median of the sample. And the median is the 50th percentile. Last time we learned that you can apply the percentile function. You have to enter the first argument is which percentile you want. And then you have to enter the array of data. And the array of data are the total compensations of the new sample, the resample. So this function returns one bootstrapped median. And, we ran it a few times and it keeps changing. Okay, so now you want to know how much it varies. And after this, the procedure is almost always the same. It is computation for iteration. You specify a number of iterations, you make a empty collection array, you run your for loop, appending your new simulated value to your collection array every time, and remembering to rename that collection array to be your longer one. Now, I have said this, and a lot of you are thinking, okay, we've done this 100 times. Stop telling me I know how to do this. So I will actually stop telling you. But I want you to notice, when you are bootstrapping in the code, where is the bootstrap? It's here in defining that single one bootstrap statistic. This for loop is exactly the same as the for loop that you have been writing since chapter 10. Nothing has changed. The resample values still count as statistics, yes, because they are calculated based on the sample. You can turn the for loop into a function, no problem. But it's good to have, when you're just learning, it's good to have the loop in front of you. All right, so we're going to run this thing, and we are going to take we're going to have an array of 3,000 generated medians. So, to the person who needs this number, you can go and you can give them the 3,000 generated medians, and they're going to come after you with a pitchfork, because they don't want 3,000 numbers from you. They want, give me some reasonable sense of how big this number is. So we're going to take the middle 95% of these bootstrap estimates. Middle 95% means 5% are on the outside. We are going to leave out 2.5% on each side. And so we are going to calculate percentiles. Left end is going to be the 2.5 percentile applied to what array? Yeah, it's the collection array in which you collected all your bootstrapped statistics. So great. And so for the right end, we have to leave out 2.5% from the right-hand side. And so we will end up at the 97.5th percentile. And okay, so this interval that we got was 126 to 137 roughly. And oh, look, we got lucky. This population parameter happens to be in that interval. And so let's visualize that. Why? No, I don't want to run the thing again. I ran the wrong cell. That is very irritating. I'm going to get a different interval. Sorry. Maybe I'll just, okay, fine. I'll get a different interval. Here. There's a visualization. Okay. Now, in this visualization, what's the good news? Why are we splitting 100 into 2.5 and 97.5? We have decided to take the middle 95%. So we have to define how to get that. So if in the middle is 95%, we are saying we have 2.5% on either side. Yes, the good news about this is that the interval contains the parameter. What's the bad news? The bad news is typically we won't know where the parameter is. Okay, so we just have to see, we have to see how, well, we won't actually know. And so there is always this sense that you could be off. And a lot of people were asking that last time, that we could be off. And so I'm going to stop sharing for just a moment, and I'm going to ask you, why could this method, what is a reason this method could be off? We might need more samples. Our original sample was bad. Our original sample was bad. Our original sample is not a good representation. That would be the problem, right? Because if your original sample represents the population, it's very intuitive to understand that this method would produce a good interval. But the original sample itself is random. And so now you could have an issue there. So based on what we know about random samples, what would you say? Is there a high probability that the original sample is bad, or is there a low probability that the original sample is bad? Low. By what rule? What is the thing that tells you? The law of averages, the law of large numbers, law of averages. That tells you with high probability, your sample is going to look like the population. Okay, but high probability, low probability, we've got a 95% floating around. Let's just see what that means. So what I'm going to do is I'm going to share my screen again. Can I explain that again? Yes. So the distribution of the original sample is likely to look like the population, but it is not certain to look like the population. There is some small chance that it looks different from the population, in which case all our estimates are going to be off. So we're trying to figure out, roughly how often can that original sample be bad, because that's when we're in trouble. So what we have to do is repeat the entire process. Draw an original sample, run the bootstrap, get an interval, then go all the way to the start, draw another original sample, run the bootstrap, draw another interval, and so on. And well, I did that. And before we proceed, let me explain why you don't have this notebook. Can anybody give me a sense of why I'm not asking all of you to run this simulation? We're going to do this 100 times, right? It's going to crash. Exactly. It's going to have to do a ton of resampling. And if you guys all do it, then life is going to be hard. And in fact, even if I do it in real time, we are going to have to wait so long, it's not worth it. And my computer will sound like it's taking off for outer space. So I ran this thing. And so I just want to point out that we have the same table and the parameter is the median, no change. And so now we are going to assess this. Okay, so there's going to be some original sample, and there is going to be, we're going to specify a number of repetitions, which I think I took to be, well, I'll see in a minute. How did I run this? I took to be about 3,000 repetitions. Okay, so we are going to draw the original sample, and then we will bootstrap the sample, and we will find a bootstrap median from the original sample. We're going to do that whole process 100 times. So we're going to get 100 intervals. All right. I'm saying we're going to get as though we're going to do it in the future. This is actually past tense. And so I've got, yeah, Lawrence is very upset with me because I'm not writing functions. But yes, this you could merge the whole thing into a function. So I'm now going to get 100 intervals. Okay, you can see 10 of them. You can see 10 of them, and 90 of them you can't see. Now, what are we going to do? We are going, when is an interval a good interval? Anybody? What intervals do we like? When it contains the parameter, exactly. And we are in this artificial world when we happen to know the parameter. The parameter is what we are calling population median. It's this number here. In the real world, we will not know the parameter, but while we do know the parameter, why don't we just see how many of them are good? So we need to count the number of intervals where the left end is below the population median and the right end is above the population median. Okay, so that is the number that I counted. Out of my 100 intervals, I got 95 that were good. And I was delighted with this because, yes, these samples are taken from the original population in exactly the same way as we took the sample that we called our sample. Okay, so we got exactly 95 of them were good. If you run it again, you may not get exactly 95, you might get 92 or 96, but you won't be very far off. To see how far off you might be, please take 140. or perhaps CS70 will do it for you. But it'll be, somewhere in the 90s. So you'll get a lot of good intervals if you repeat this process. By theory, you should get 95%, roughly 95% that are good. And so we drew all of those. Actually, I can go back to my slides here. We drew all of the intervals for you. So each interval is an interval of estimates of the parameter. It is based on random sampling, so it could be off, right? That 95% is called the confidence level. You can change that. The higher the level, the wider the interval. If you want more confidence from the same data, you're going to have to give yourself more wiggle room. A good interval is one that contains the parameter, and the confidence is in the process that creates the interval. It gives you a good interval about 95% of the time. And wait, where's my picture? There it is. Okay. So each of those yellow lines is one of the intervals. We drew 100 of them. We created 100 of them. I've just drawn the picture of all of them. The green dot on the number line is very, very important. That is the parameter. And it is crucial that you imagine it as a nail hammered into the number line. It cannot move. It is fixed. Sometimes you might not know where it is. But that doesn't mean it can move, right? Very often you won't know where it is, but it's a fixed number. So the good ones are the ones that cross that green line. And of course, I couldn't put all the intervals on top of each other. You wouldn't know what they were. So I basically jittered them, right? Here's interval number 1, interval number 2, interval number 3, 4, 5, 6, etc. Okay, so which ones are the bad ones? The bad ones are the ones that don't cross the green line. So I'm just going up, good, 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 good. Here's a bad one. The bad one is everyone where you see daylight around the green line. Okay, before I move further, is it clear what the picture is representing? Or do you have questions about what the picture is representing? We created 100 intervals. We have drawn 100 intervals. And now it is really important for us to count the bad ones. And I see 1, 2, 3, 4, and 5. And remember when we counted the good ones in our interval, this is just a made up graph. I just stacked a whole bunch of intervals, one on top of the other, just so that you could see. When we counted the good intervals, then there were 95, and that's what you can see from the picture. Can we only execute this process if we resample from the population? You can execute this process if you have any method of trying to estimate by intervals. Our method happened to be resampling from the population. That is why that is what we replicated. There are some long and some short intervals. Actually, they're actually not that far in length. Yes, some are long, some are short. And they'll differ a little bit. Give me a couple of weeks and you will have some measures of how wide they're going to be. How do we know what the parameter is? Because we're in an artificial situation where we started with the population. We actually calculated the parameter first. We know in this situation, we know where the parameter is. Typically, you will not. I want to get to that in just a minute. Okay, are the tiny space these? The interval is here. This interval is here. The interval is only the yellow bit. That's an interval. All right. And so the fact that there is space around the green tells you that it didn't cover the parameter. That means it's a bad interval. The left end and the right end are the two ends of the interval. Right? You have your middle 95% of your empirical values. And so the left end of that will be different. It will be smaller than the right end. Okay. So there we were in a situation where we knew the parameter. So this is basically a way for us to show you, demonstrate to you that the process that we have outlined generates a good interval 95% of the time. Okay, you can run this again with a different data set. You'll get the same thing as long as you start with a big random sample. You'll get the same rule. The confidence is in the process. So now we are going to work in a situation where we actually don't know what the parameter is. That's a realistic situation. And then you will get an interval and you will not know whether or not it contains the parameter. Life isn't that great, but you will know that the process generates a good interval 95% of the time by what we have just done. And so therefore, that's the amount of trust that you have in your interval, which is way better than guessing at random. Okay, so let me go now to a situation that you're correct. We are just showing that the method works. So we're going to go to a situation where we had data from a genuine random sample. So this is the births table that you've seen before. And we are going to look at the average age of the mothers. Okay. Okay, so the thing that I'm looking at, is it a sample or a population? Read the cell. Right up here, this cell, the table, what's the comment? Random sample, the thing that you're looking at is the sample. The population was huge, we do not have the population. This is realistic, okay? We have decided that we are interested in the average age of the mothers. In this sample, it happened to be around 27, all right? Do we know what it is in the population? We do not. We don't have the population. So we're going to try and use this sample to give us some sense of what the average age is like in the population. It's not going to be exactly this. It's going to be off. Okay. So what's your plan for estimating the parameter? What are we going to do? You tell me and I'll type it in. We have this one sample. It has, actually, give me one moment. Is it a large sample? It's huge. It's 1,200. Yes, we are going to bootstrap. And then find the mean of each. Right? And then repeat this process. And then once you get the, if you want a 95% confidence interval, then you graph all the means, yes. And what's your interval going to be? Package into array. Yes. Interval, so 95% confidence interval is 2.5 to 97.5 percentiles of the array. Okay, this is the plan. And the only thing that will change if you're doing it in any other situation is whether you're finding the mean or the median or the proportion of smokers or whatever will depend on what parameter you're interested in. Otherwise, the process is exactly the same. Okay, so we are going to write an interval. You don't need to graph it, but graphing it will show us something interesting. So, okay, what's the first step? If I want to return one bootstrapped mean, what do I have to do? Step one. Look at your plan. Your plan said bootstrap the births sample. So I have to do something to births. What do I have to do? I have to do sample. That's the bootstrap sample. I got to call it something. I'm going to call it resample. Okay. And now what do I have to do to this? I have to take a mean of something. What? Of what? The mean of what? Resample. And then dot column. Yes, and the column is called maternal age. Okay, so I'm going to return the average age in this bootstrap sample. Wonderful. And then I'm going to run a for loop, just as I did before. And I apologize to Lawrence for not having put it in a function, but I'm just not going to. If you go back and look, you will see it's the same for loop as before. It's just we're calling it means instead of medians because, well, they are means. Okay, so you're going to have this 95% confidence interval is your middle 95%. You know that we're going to take the 2.5th and 97.5th percentiles. Okay, we're still generating our means. Okay, so now look, the interval is 26.89 to 27.54. Okay, and so we're drawing that. Okay, there you have a picture of the real world. What is the difference between this and the similar picture that we drew for the total compensations? No parameter. No parameter. Yeah, we don't know where it is. We are trusting that the process in general, 95% of the time gives us a good interval. We just have to trust that this is a good interval. Okay, I just want to show you something that if you wanted a 90% confidence interval, you would do exactly the same thing. The only thing that would change would be which percentiles you look at. Can somebody tell me which percentiles? 90% in the middle, so 10% outside. So you would take the 5th percentile, and what's the other one going to be? Yeah, you leave out 95 on the other side, and so you'll get a different set of this intervals. And if you draw that, okay, what is the same and what is the difference? What is different between these two? The histogram is exactly the same, right? It's exactly the same data. The interval is shorter, and you have less confidence in it, right? This process, the second process, generates a good interval 90% of the time. So basically, there's no such thing as a free lunch. If you want a narrow interval that you want to say, okay, I'm going to tell you that the ages are just in this tiny little region from the same data, then you probably have less confidence. All right. And so now you know how to create bootstrap. Actually, that's a really good question. Did you use the original sample mean for anything? Absolutely not. That is an excellent question. The original sample mean has no particular status in this. The original sample was what we used to generate all our bootstrap samples. There are other methods that start with the original sample mean and bootstrap errors and so on, but our method is called the bootstrap percentile method, and it doesn't do that. Works though. In the situations in which you start with a large sample and so on. So I'll talk about that in just a moment. Okay, use methods appropriately. So the bootstrap is great and it's very tempting, but we have to be careful. It applies only in certain situations. Okay, so if you are making an estimate based on a sample and then you're sampling from that sample, if your parameter depends on rare elements of the population, you might not get it in your original sample, and you definitely might not get it in your next sample. So don't do it for, the 99th percentile or the min or the max. Okay, this is not going to work. The theory says that this middle 95% method is justified only if you have a roughly bell shape. And how do you know it has a roughly bell shape? Well, you look at it. Okay, your empirical distribution, if that's roughly bell shaped, then you're probably fine. Don't use it if the original sample is small. You know that, because if the original sample is small, it might not represent the data in the population. Okay, so what we've done is we have used our method in a situation where our original sample was large. It was about 1200. This distribution is not normal, but that's not what we're concerned about. So we did a bootstrap, and our distribution of bootstrapped means is approximately bell-shaped. Keep that in mind, right? This is something that we have noticed, and there's a real reason as to why this is, and we're going to spend a little time talking about that. Bell-shaped means looks like the Liberty Bell, that goes up like that and comes down. Just imagine the kind of bell that you ring. That's what it looks like. And there's a formal definition that we'll talk about later. Okay, so this empirical distribution came out to be bell-shaped, and so therefore for this situation, the method works. So this was a fine thing to do. And now what I want to do is I want to look at this interval. We got this interval 26.89 to 27.54. All right, so it's roughly 26.9 to 27.5. And we're going to try and interpret the interval. Roughly 26.9 to 27.6 is your interval. Okay. Okay. So we want to use this interval. Can you say the following? About 95% of the mothers in the population had ages in that range. Is that what this interval is saying? And before you answer that question, just look at that interval, right? Is it wide? Is it narrow? What do you think? Wide or narrow? It's very narrow, right? Those ages are just around 27 and a half years old. So it is just not realistic that 95% of the mothers in your population in the hospital are just 27 years old. So that's not what it's saying. So then what is it for? It's for one thing and one thing only. What was the original goal of this? It was estimating the average age in the population, right? We are saying that in the population from which you got the sample, the average age of the mothers, we think with some degree of confidence, is in this range, right? It's not so much about the confidence, but the fact that this is estimating a parameter. It is not telling you a distribution in the sample. It's telling you how big the parameter is. So the average age in the population, this is our guess for that number. And so just to go back and take a look at our distribution of maternal ages, 27 is somewhere here, right? Maternal ages are very widely spread out. All right, what we're saying is that the average of the population is somewhere in this region. The average in the sample is exactly 27.22, but we're saying the average of the population is just around that. And we have quantified around. So it is very important to note that the confidence interval allows you to quantify two things. It allows you to quantify around, but it also measures the frequency with which your process is off. That you can say that if I do this process, I know the fraction of times I'm going to be off. That is quite important. No, it should not be 95% of the average ages of the mothers. The mothers in the population have exactly one average age. It's a fixed set of people that had one average age when the sample was taken. That is the number that we are trying to estimate. We are not trying to estimate a whole bunch of numbers. We are just trying to estimate that one number. And we're saying that one number is in this interval. Okay, and now I want to ask you a more subtle question. If you increase the confidence, it decreases the chance of being wrong, right? If I say I want a 99% confidence interval, right, my interval is just going to be wider, right? And it's going to be off 1% of the time instead of 5% of the time. But the estimate is also going to be less sharp, right? You're just going to have more wiggle room. From the same data, there's only so much information that you have. The parameter represents one thing and one thing only. It is the average age of the mothers in the population. The parameter has nothing to do with these data. Increase confidence, decrease error, decrease the chance of error. However, also increase width of interval. That's what we saw. All right. So now I want you, can you really ever say 100% confidence interval? You can, but it won't be useful. These are ages of mothers who gave birth. Right? I can just walk up, not take any data and say, okay, I'll give you 100% confidence interval. 8 years old to 100 years old, right? I'm just going to say the average age of the mothers in the population is in that range. And you know, it's going to be 100% confidence. It's totally useless though. So what you're trying to do is to get as narrow an interval as you can get with some degree of confidence. Okay, so now this issue is subtle. Please pay attention. So we've got our interval, all right? Can I say that there's 95% chance that that population average is in this range? Remember that population average, that was that green dot that we can't see, but it's nailed into the line. Don't answer quickly. The green dot is nailed into the line. We don't know where it is, but it's nailed. It is not here some days and somewhere else on other days. It is a fixed number. The average is fixed, and these two numbers are also fixed. These are not waving all about. All right, so this particular interval either always contains that fixed parameter or never contains that fixed parameter. There are no probabilities involved here. So what is the confidence in? The confidence is in the process that generates the interval. The process creates good intervals 95% of the time. And this is something that you have to be, it takes a while to get used to. And the thing that you have to say is, I've got this one interval, I have created it using this process, I'm giving it to you to use. Be aware that I don't know if this particular one is good, but the process is good a big fraction of the time. And so this is what I'm going to do. With incomplete information, there is no way that you can do a completely correct answer every single time. And with this information that we have, it's actually very hard to do better than what we have done. Okay, so I want to go back now. So we're finding ways in which to interpret confidence intervals and ways in which not to interpret confidence intervals. I want to go back and ask you another question. Okay, so we have a, let me redraw the 95% confidence interval again. Okay, so this interval goes from about, just 26 and a bit to 27 and a bit, okay? I'm going to ask you an artificial question, but learning how to answer that artificial question will help us answer a more realistic question on Friday. Look at this interval. Supposing I ask you this, I want you to test a pair of hypotheses. Null hypothesis, the average age in the population is 25 years. Our sample was different due to chance. Alternative hypothesis, the average age in the population is not 25 years. If you're just looking at this picture and you don't know anything about anything, but you're looking at this picture, which one will you take? Population average equals 25 or population average not equals 25? You will take not, because why? Because you're looking at this interval and there's no 25 in it, right? 25 is all the way out here. There's no 25 in it. And in fact, there's a theory that says that performing that test, so null hypothesis, average age in the population is 25 years, random sample is different due to chance. Alternative, average age is not 25 years. If you want to do this using a 5% cutoff, you can make a 95% confidence interval for your average age. Look to see whether your null number is in there. So 25, is it in there or not? Well, it's not in there. Go with the alternative. There's a theory that says that in general, if you have this kind of bell-shaped curve and so on, you have this kind of situation, then this is equivalent to doing that hypothesis test. And I say it's better than doing that hypothesis test. Why? Because the hypothesis test simply says, is it 25 years or not? So the hypothesis test concludes, okay, based on these data, we're going to say not. Okay, so if it's not 25 years, it immediately begs a question. Well, what is it then? And that's what the confidence interval answers. We think that the average age in the population is in this particular numerical interval. Okay, so you can use the hypothesis test, you can use the confidence interval to do this particular test of hypotheses, which is null hypothesis, population parameter equals specified number. Alternative hypothesis, population parameter not equal to that specified number. The confidence interval will do that for you. Can you tell me if I wanted to it's when is it appropriate to do this bootstrap method? So we had a slide that says when the bootstrap, you have to start with a large sample and your empirical distribution at the end should be roughly bell-shaped as we have here. If I wanted to use 1% as the cutoff for the p-value, then how would I change my calculation? What would I have to do? 5% cutoff for the p-value, we used a 95% interval. 1% cutoff for the p-value, what interval would you use? You'd use a 99% interval, exactly. Exact same data, you don't have to recalculate anything. You just use a different interval, the wider one. All good? Okay, on the dot of 11, we are done. And I will